Hello viewers, in today's session we are going to discuss an important differential equation involving the Dirac delta function, right? So here we have to solve this differential equation which is y prime plus y is equal to delta of t minus 1, where the initial conditions are y of 0 is equal to 0, right? So in this class we'll learn how we can solve these type of differential equations involving the Dirac delta function using the concept of Laplace transform and the inverse Laplace transform, right? So before solving this differential equation, let us recall an important result from inverse Laplace transform, right? Because that result is going to be a very important result while solving this differential equation. So the result is the inverse Laplace transform of this function, that is e raised to minus as. F of s is given by f of t minus a multiplied with h of t minus a, right? Where this h is the famous Heaviside unit step function, right? So this result would be used while solving this differential equation. So now let us rewrite this differential equation as d by dt of y of t plus y of t, and here we have delta of t minus 1, right? So let us take the Laplace transform of both sides. So the Laplace transform is given by L, and here we have y prime of t, then we have the Laplace transform of y of t, and here we have the Laplace transform of delta of t minus 1, right? So here we are using the notation y prime of t for y prime, and for y we are writing y of t, right? Okay, so now let us use another important result from Laplace transform of derivatives, because here we have the Laplace transform of the derivative of y of t. So now the Laplace transform of f prime of t is given by s times f of s minus f of 0, right? So this is the direct result which we are going to use here. So the Laplace transform of the derivative of f of t is given by s times the Laplace transform of the function f of t minus the value of the function at 0, right? So here we have the Laplace transform of y prime of t, right? So using this result, we can now write here s times the Laplace transform of the function f of t. So here for y prime of t, we have the function y of t. So here we can write the y of s, right? So here we are using the notation capital Y of s for the Laplace transform of this function y of t, right? So the Laplace transform of y of t can be written as capital Y of s, and then we have f of 0. So for f of 0 we can write y of 0, right? So this is the term for the Laplace transform of y prime of t, and then the Laplace transform of y of t can be replaced by this notation. So here we have y of s, and here we have Laplace transform of the delta function, and we know that the Laplace transform of the function, that is delta of t minus a, is given by e raised to minus s times a, right? So here we'll write minus s, and for a we can take the value as 1, right? So here we have minus s times 1, so this is e raised to minus s. So now using this condition, that is y of 0 is equal to 0, this term is 0. So we have s times y of s minus 0 plus y of s is equal to e raised to minus s, right? So here taking y of s common from these two terms, we have y of s, and here we have s plus 1, and this is e raised to minus s. So we can now write y of s is equal to e raised to minus s over s plus 1. And remember, y of s is the Laplace transform of the function y of t. So now we can also write here the Laplace transform of the function y of t, right? So now we have obtained the Laplace transform of the function y of t as e raised to minus s over s plus 1, right? So let us now compare this expression with this one, right? Because see, from here we can write y of t as the inverse Laplace transform of this function, that is e raised to minus s over s plus 1, right? So from here we have obtained the function y of t as the inverse Laplace transform of this function. So let us rewrite this function, which is a function of s. We can write L inverse, and here we have e raised to minus s times, and here we have 1 over s plus 1, right? So now we have obtained this expression similar to this one, right? Because see, here we have L inverse, and here we have e raised to minus as f of s, right? So if we compare these two expressions, then the value of a is 1, right? So the value of a is 1, and f of s is given by 1 over s plus 1, right? So the Laplace transform of some function is f of s is equal to 1 over s plus 1. So let us find out that function whose Laplace transform is 1 over s plus 1. So now we know that the Laplace transform of the function e raised to at is given by 1 over s minus a, right? So if we take a is equal to here a minus 1, then the Laplace transform of e raised to minus t is given by 1 over s minus minus 1, that is 1 over s plus 1, right? So here we have 1 over s plus 1. So it implies that this is our Laplace transform of e raised to minus t. So the function f of t is now e raised to minus t, right? So now f of s can be written as L of f of t, and f of t is e raised to minus t, right? So now this expression, that is the inverse Laplace transform of e raised to minus as f of s, is equal to the product of these two functions, right? So this expression, that is our function y of t, is now equal to f of t minus a times h of t minus a, right? And our function f of t is e raised to minus t, and the value of a is equal to 1 here, because here we have minus s times 1. So we have f of t minus 1, and here we have h of t minus 1, and f of t minus 1 can be obtained from here by replacing this t by t minus 1. So we have e raised to minus t minus 1 times h of t minus 1, where this function h of t minus 1 is the Heaviside unit step function. So now our function y of t can be written as e raised to minus t plus 1 times h of t minus 1, right? So viewers, this is the solution of this differential equation containing the Dirac delta function, right? Because the purpose of solving a differential equation is to get the function. So here our function y of t is equal to e raised to minus t plus 1 times h of t minus 1. So viewers, the required solution of this differential equation is given by this expression, and here I would like to mention one important thing, that this expression, that is f of t minus a times h of t minus a, can also be expressed like this, that is the inverse Laplace transform of e raised to minus as f of s is equal to this expression, and this expression can also be expressed like this, that is f of t minus a for t greater than a, and this inverse Laplace transform is 0 when t is less than a, right? So now using this form, we can also express our solution as y of t is equal to f of t minus a, that is f of t minus 1 for t greater than 1 and 0 for t less than 1, right? And f of t minus 1 can be written as e raised to minus t minus 1 for t greater than 1, and here we have 0 for t less than 1, right? So both these forms, that is this form and this form, both are equivalent. Hello viewers. In today's session, we are going to discuss another differential equation involving the famous Dirac delta function, right? So here in this class, we are going to solve this differential equation, that is y prime minus y is equal to delta of t minus 2, and the initial conditions are given as y of 0 is equal to minus 1, right? So here we'll solve this differential equation involving the delta function by using the concept of Laplace transform and the inverse Laplace transform, right? And moreover, we'll also make use of some direct results from inverse Laplace transform, right? So let us start. So here we are given y prime minus y is equal to delta of t minus 2. So let us rewrite this differential equation as d by dt of y of t minus y of t is equal to delta of t minus 2, right? Okay, now taking the Laplace transform of both sides, what we will do, we'll write L, and then we have d by dt of y of t, which is simply y prime of t, right? And here we have the Laplace transform of y of t, and here we have the Laplace transform of the delta function, that is delta of t minus 2, right? Okay, now let us see some notations here. We'll denote the Laplace transform of the function y of t as capital Y of s, right? And we know that the Laplace transform of the delta function, that is delta of say t minus a, is given by e raised to minus as, right? Okay, And one more result from the derivatives of Laplace transform, we know that L of f prime of t is given by s and f of s minus f of 0, right? So the Laplace transform of the first derivative of f of t is given by the product of s and the Laplace transform of the function, say f of t, because the Laplace transform of f of t is denoted by f of s, right? And then we have f of 0. It means for t is equal to 0, we have f of 0. So using this result for y prime of t, we can now write here s times the Laplace transform of f of t, and here for f of s we can write the Laplace transform of y of t, that is capital Y of s, right? And then we have here y of 0, because here we have f of 0. So we can write here y of 0, and the Laplace transform of y of t is y of s, and here the Laplace transform of delta of t minus 2 is given by e raised to minus as, and here the value of a is 2, so we have minus 2s, right? So now we have this equation, so let us collect the like terms. So here we have s times the Laplace transform of y of t. So taking these two terms, we have s minus 1 y of s, and y of 0 is minus 1. So here we have minus 1 e raised to minus 2s, and we have s minus 1 y of s is equal to e raised to minus 2s, and this is minus minus plus. So if we take 1 to the right hand side, we have minus 1, right? So now we have y of s is equal to e raised to minus 2s minus 1 over s minus 1, right? And y of s, that is capital Y of s, is the Laplace transform of the function y of t, right? Now this function y of t can now be obtained by taking the inverse Laplace transform of this function, right? So y of t is L inverse, and here we have e raised to minus 2s minus 1 over s minus 1, right? So the purpose of solving a differential equation is to find out the function, right? And here we have the function now, that is y of t can be obtained by taking the inverse Laplace transform of this function e raised to minus 2s minus 1 over s minus 1, right? So let us write this expression as y of t is equal to L inverse, and we can now write e raised to minus 2s over s minus 1 minus 1 over s minus 1. So we can split this term as a sum of or difference of these two terms, right? And now we know that the inverse Laplace transform follows the linearity property. So we can now write y of t is equal to the inverse Laplace transform of e raised to minus 2s over s minus 1, and then we have L inverse and the Laplace transform of 1 over s minus 1, right? So now our function y of t can be given by this expression. So now let us use an important result from inverse Laplace transform, right? So we know that the inverse Laplace transform of the function e raised to minus as f of s is given by the product of the function f of t minus a and h of t minus a, right? This is an important result while solving Laplace, solving differential equations of this type, right? So always remember this result. And here f of t minus a is the function which is associated with the Laplace transform or the inverse Laplace transform of f of s, and h of t minus a is the Heaviside unit step function. So now to get the inverse Laplace transform of this function, we'll make use of this result, right? Because see, here we can write this expression as L inverse, and then we have e raised to minus 2s times f of s, and f of s is 1 over s minus 1, right? So here this quantity, that is f of s, is given by 1 over s minus 1, and from the Laplace transform we know that the Laplace transform of e raised to t is given by 1 over s minus 1, because we know this result, that is the Laplace transform of e raised to at, is given by 1 over s minus a, right? So the Laplace transform of e raised to t is 1 over s minus 1. So this is our f of s. So now here we can write this term, that is f of t is given by e raised to t, right? So this is our function f of t. So now the value of the inverse Laplace transform of this function e raised to minus 2s over 1 over s minus 1 can be written with the help of this result. So we have f of t minus a, and our function f of t is e raised to t, right? Because here the function e raised to t has the transform as 1 over s minus 1, right? So we can now write this inverse Laplace transform as f of t minus, here we have the value of a as 2, so we have f of 2 minus 1, then we have h of t minus 2, right? Because if we compare this term with this one, then the value of a is given by 2, right? So the value of this expression is given by the product of these two functions, f of t minus 2 times h of t minus 2, and f of t is e raised to t. So now we can write as e raised to t minus 2 times h of t minus 2, right? And the value of this expression, that is L inverse of 1 over s minus 1, is given by e raised to t by this expression, right? So now our function y of t is given by e raised to t minus 2 h t minus 2 minus, and here we have e raised to t, right? So this is the solution of this differential equation when the initial conditions are y of 0 is equal to minus 1. So viewers, this is how by making use of this important result, we can solve these kind of differential equations involving the Dirac delta function. Hello viewers, in today's session we are going to discuss another differential equation containing the famous Dirac delta function, right? So here we have to solve this initial value problem in which we are given this differential equation, that is y prime is equal to delta of t minus 2 pi with the conditions y of 0 is equal to pi, right? So in this session we'll see how we can solve the differential equations involving the Dirac delta function and with the initial conditions, right? So here we'll make use of the method of Laplace transforms, and then we'll use some standard results from inverse Laplace transform, right? So let us see how we can solve these kind of differential equations. So here we are given y prime is equal to delta of t minus 2 pi, which can also be written like this, right? Y prime of t is equal to delta of t minus 2 pi, right? Where y prime of t is the derivative of y of t with respect to t. So now let us take the Laplace transform of both sides, right? So we have L of y prime of t is equal to L of delta of t minus 2 pi, right? Now to find out the Laplace transform of derivative of a function, we can use this result, that is the Laplace transform of f prime of t is given by s times f of s, where f of s is the Laplace transform of the function f of t, right? So here the notations are important, and s times f of s minus f of 0, right? Where f of 0 is this the value of the function at t is equal to 0. So here we are using the capital F for this function, or we can also replace this f of t, that is small f, by capital F, right? So this is the formula for the Laplace transform of f prime of t, which is s times f of s minus f of 0, right? So here L of y prime of t can be written as s times the Laplace transform of y of t. So here we can write y of s minus y of 0, right? So using this result, we can write the Laplace transform of y prime of t s times y of s, where y of s is the Laplace transform of y of t, right? And here the Laplace transform of this delta function may be written as e raised to minus 2 pi s, because we know that the Laplace transform of the delta of t minus a is given by e raised to minus as, right? So now we have this equation. Now y of 0 is given as pi, so we can now write s y of s minus pi is equal to e raised to minus 2 pi s. Now taking minus f minus pi to this side, we can write y times y of s is equal to pi plus e raised to minus 2 pi s. So now let us write y of s is equal to pi over s. Dividing these two terms by s, we have e raised to minus 2 pi s over s, right? Now y of s is equal to the Laplace transform of the function y of t. So here we can write L of y of t, right? So now to get the value of the function y of t, which is our objective to solve this differential equation, because when we solve a differential equation, our aim is to find out the function. So here we have y of t. So y of t can be written as the inverse Laplace transform of this function, that is pi over s plus e raised to minus 2 pi s over s. So now the inverse Laplace transform follows the linearity property. So we can now write L inverse, and here we have pi over s. Then we have L inverse, and here we have e raised to minus 2 pi s over s, right? Now here we can take this pi outside. So we have pi, and then we have L inverse of 1 over s, and here we have L inverse, and we can write it as e raised to minus 2 pi s times 1 over s, right? So now our function y of t can be given by this equation number 2. So now here we'll make use of two important result from the inverse Laplace transform, right? See, we know that the Laplace transform of 1 is equal to 1 over s, right? And we can now write the inverse Laplace transform of 1 over s as 1, right? So here we have 1, so we can now write y of t is equal to pi times 1, and to get the value of this expression, we'll again make use of an important result from inverse Laplace transform, that is L inverse of e raised to minus as, and here we have say f of s is given by f of t minus a times h of t minus a, right? This is an important result. So the inverse Laplace transform of this function, that is e raised to minus as fs, is equal to f of t minus a times the Heaviside unit step function h of t minus a, where f of s is the Laplace transform of the function f of t, right? So here we have f of t. So now here we have L inverse of e raised to minus 2 pi s times 1 over s. So comparing this expression with this one, the value of a is 2 pi, right? The value of a is 2 pi, and f of s is given by 1 over s, right? So here f of s is 1 over s, so it implies that L of f of t is given by 1 over s. So from this result we can easily see that the value of this function f of t is equal to 1, right? So f of t is equal to 1 because the Laplace transform of 1 is 1 over s, right? So now using this result, we can write the value of this inverse Laplace transform as f of, so we have f of t minus a is 2 pi, and here we have h of t minus 2 pi, right? Now f of t minus 2 pi can be obtained from this function. So here we have f of t is equal to 1. So f of t minus 2 pi is equal to 1, because here f of t is independent of t, right? So now we have y of t is equal to pi, and then we have here 1 times h of t minus 2 pi, where h is the Heaviside unit step function. So now we can write y of t is equal to pi plus h times t minus 2 pi, right? So viewers, this is the solution of this differential equation.